was an owner of portions of the Falcon Heavy rocket thrust structure. This is the structure that holds the entire rocket up on the launch pad and has all the rocket engines mounted to it. My last year at SpaceX, I was responsible for the combustion chamber nozzle, the Raptor engine. The part where the fire comes out, I kept solving hard problems and looking for the next hard problem to solve, and I kept thinking about what could be next. And climate change is this massive problem rearing its head in the world. I founded the company in March last year. After doing a bit more research and making it in chunks that you can build in a factory, you can now do it as a repeatable process on an assembly line that ships large chunks to a site, and your on-site construction time is completely collapsed. These projects today are over 18 months long to go build a surface equipment facility. Our target is to do it in 2 weeks.
Welcome to Geothermal Unleashed, the podcast where we dive into the frontier of geothermal energy and its role in the global energy transition. I'm Elizabeth Cambre with the Valorec New Energies team, and I'm here to help spotlight the innovation, technologies, and the stories driving geothermal forward. And today I'm very excited to welcome my guest, Spencer Jackson, who's the founder and CEO of Critical Energy. So Spencer and I first met on a fabulous tour. We were headed to the Puna geothermal power plant in Hawaii when we were going to the Geothermal Rising conference last year, and we had a fabulous conversation. So I want to just welcome you, Spencer. It's nice to catch up. And why don't we get things kicked off? I want to hear your story about how you have transitioned from working from SpaceX to working in the geothermal industry. And I want to hear more about your background. So if you give us a little bit about your education and just your career, overall career, and how you came to found Critical Energy.
Yeah, for sure. There's a lot there to unpack, so I hope you don't mind sitting back while I talk a little longer than I like to. Thanks for having me on here, Elizabeth. It's great to be invited. So my journey, I grew up in Minnesota originally. My parents are both mechanical engineers, so they knew I liked to build things from an early age and watching me build things. Why SpaceX? My dream became to work on rockets in 2010. As a sophomore in high school, there was a Popular Science magazine article that said this is the year the commercial space industry takes off. And at that time, I thought only NASA and the government worked on rockets. And I've always liked to solve hard problems, but I wasn't really sure where I wanted to take my career until that moment when I discovered SpaceX existed. So I built my whole undergraduate career toward getting to SpaceX. I worked on race cars for 4 years. I was at Tesla for 6 months in 2014, SpaceX for 3 months in 2015 in avionics as an intern, and then I started full-time in Falcon Heavy structures. So I worked across avionics systems, Falcon Heavy structural mechanics. So I developed a lot of the designs for, and I was an owner of portions of the Falcon Heavy rocket thrust structure. So this is the structure that holds the entire rocket up on the launch pad and has all the rocket engines mounted to it. And then I managed a structural qualification campaign for the entire Falcon Heavy center core, which is like a 164-foot tall booster. It sees millions of pounds of load. And we developed a campaign in Texas to be able to structurally qualify it for flight. So how do you simulate all of the loads a rocket might see in a normal launch or otherwise an off-nominal situation so that it won't explode, won't destroy itself on the launch pad or on ascent. Did that for a while, and then I moved over to Starship heat shield. I designed all the high temperature thermal seals for reentry for Starship. So they're called the flap seals. So how do you interface between the vehicle flaps and the vehicle body itself without melting on reentry? That's thousands of degrees Kelvin gas flowing over a reusable orbital class reentry vehicle that is Starship. It was a fun, difficult problem. We figured out how to make a first of a kind flap seal designs, iterated on them, and then built a production line. And I was by hand installing 180 feet in the air in a boom lift, the first version of it on the rocket, the launch pad in South Texas. I moved over there to Raptor. My last year at SpaceX, I was responsible for the combustion chamber nozzle, the Raptor engine. So for those that aren't as obsessed with rockets, the rocket and the part where the fire comes out of a rocket, so I was responsible for that for about a year. So managed the technical design aspects of that, of how do you basically work with a production team to productionize it. And we hit multiple engines a day on the SpaceX Raptor production line there. My work in SpaceX, I kind of got bored after about 7 years. I kept solving hard problems and looking for the next hard problem to solve, and I kept thinking about what could be next. And climate change is this massive problem rearing its head in the world, and energy is roughly 5/6 of all human emissions. So thinking about what could I do next, when I was in middle school in 2006, my parents started a company, grew a small business, and then sold it. And that was extremely inspirational for me to see. And I kind of put the bug where I knew one day I wanted to start my own company. I wasn't sure when, but I knew I had to try at some point. And so by the time I was ready to leave SpaceX, it seemed like the right time to try. I had an idea for a startup in the energy space. I approached a serial founder in the Bay Area and asked him for advice. So how do you think about starting a company? He, after a long conversation, turned to me and said, well, why don't you just come work for me? So I left SpaceX and joined him. He had a small VC firm. I joined him as an entrepreneur in residence for about a year to learn about energy. And it's really studying where is the energy market today and where is it moving and where are the needs that are not being addressed. If you look at the need for energy, a lot of it is 24/7, is a massive hole that we need to solve. And there aren't a whole lot of options for scalable 24/7 energy sources. One of those that I see a lot of potential in is geothermal. The opportunity to anywhere on Earth drill deep enough and hit hot rock. The opportunity to access that heat and create electricity with it. And I don't have to sell that to you. I'm sure you and your listeners are primarily pretty bought in on the whole idea of geothermal. But that's what inspired me. I went to Reno in October of 2023 to Geothermal Rising and met a lot of people in the industry and realized that the subsurface is where most people are focused. We can go after solving the surface harbor problem. How do we convert heat to electricity more cost effectively, faster deployment, potentially higher efficiency of conversion as well than is currently done, such that we can help accelerate the process that is geothermal. So that's what led me into the geothermal industry. That's kind of my background in SpaceX that got me here. I answered some of your questions. Feel free to go from there.
Your background is amazing. I can't believe you got bored working at SpaceX. That would be so much fun. Very interesting. So you first learned about geothermal 2 years ago, and here you are 2 years later with your own company, Critical Energy. I think that is so just inspiring. Can you tell me a little bit about Critical Energy? So it emphasizes modular factory-built power plants. So what does this mean? Can you talk about that?
Yeah, I founded the company in March last year after doing a bit more research. And it's about how do you completely collapse the costs and increase the scalability of the surface equipment, the deployability of it. Looking at the problem there, if you build your power plants on site piece by piece, the scalability that is you have to add more and more laborers, more and more work to continue to do that repeatedly if you're going to grow that by building modular power plants. So thinking about everything that takes to make a utility grid scale power plant and making it in chunks that you can build in a factory, you can now do it as a repeatable process on an assembly line that ships large chunks to a site, and your on-site construction time is completely collapsed. As an example, a lot of these sites projects today are over 18 months long to go build a surface equipment facility. Our target is to do it in 2 weeks for comparison. Yeah.
So can you break down for me the advantages then over your modular offer versus just traditionally going out into the field to develop the surface equipment?
Yeah, there's quite a few advantages there. One, the wellheads of geothermal are usually about 2 to 10 megawatts per wellhead. It's pretty typical. So the drilling operation effectively is already modularized. You have to put a lot of wellheads together to put together a large 30 to 50 megawatt power plant. If your drilling operations are modularized and you're drilling them one by one, wouldn't it be beneficial to install the power plants in a modular way and install them in a similar fashion? So we can scale and grow as the project scales and grows. That's a huge advantage. So if for sites that drill a first of a kind well and flow test it, they can be generating revenue or at least electricity to prove the valuability of the resource sooner than they otherwise could if you're waiting for a 30 megawatt plus plant. That's the advantage of modularity. For reference, our unit size is roughly 2 megawatts net for our first units. We'll be scaling a bit up from that on our module size, but think about single-digit megawatt modules for what Critical Energy offers. You can stack those in parallel and you can have as many units as you want on the site. So if you are developing a new geothermal site and you are anticipating it to be call it a 30 megawatt resource. So you're going to drill maybe 6 production wells to your 30 megawatts, and you have to plan this out 3 years in advance, and you're negotiating a power plant purchase agreement. The reality, when you go and drill those 6 wells and you flow test them, is that you're almost certainly not actually at 30 megawatts. You're going to either be at 26 or 34. You're never going to hit what you actually thought you were going to. So the power plant you purchased with the turbine that was tuned directly to that optimization is going to be operating off nominal. You're either going to have paid more capex than you needed to for a resource that is now operating even less efficiently than it could to do 26, or you're going to have excess flow capacity that you can't actually use in that plant.
Yeah. Okay. So I'm not an expert on power plants. What all goes into your factory built power plant? Like, what does it consist of? Can you break that down for me?
I mean, in general, these are relatively simple. It's a ranking cycle. So in our case for geothermal, the temperature range is perfect for organic working fluids. So think of it as like, the isopentanes and butanes of the world. The plant is a heat exchanger that you take heat out of the ground. So think about your big pipe diameter coming out of the ground off your wellhead, plumbing that into, for in our case, the side of a shipping container, into a series of heat exchangers, and then we give you back the brine as a cooled off fluid for return and reinjection. Our heat exchanger is extracting that heat to a closed loop fluid system that is our working fluid cycle. So it's vaporizing our working fluid to either superheated or supercritical, depending on the resource temperature, and flowing that through a series of turbine blades. So in our case, it's a multi-stage axial turbine. That is how we generate our electricity. So we're trying to maximize as much power extraction as you can from that turbine to a generator. The return flow coming out of the turbine now is a lower temperature, really low pressure fluid that we then have to flow through a series of air-cooled condensers to reject their waste heat to the air and condense it back to a liquid. We pump back through. And in our case, that's all a series of shipping container volumes that are just brought together and assembled on site.
So is this a smaller footprint then of what you would see with a typical power plant?
It is. It's our footprint is somewhere on the order of it. We'll see how big it is, but it could be as about half the size of the typical ones.
Interesting.
The largest surface area is the air-cooled condensers. So a lot of how do you make a power plant for geothermal, if you care about site size, is the design of the air-cooled condensers and being compact. What we found is that geothermal is typically kind of in the middle of nowhere for now. So site size is less impacted other than cost, right? You have land preparation cost to do that. The performance of your plants, thermodynamic performance, and the dollar per megawatt are the values that seem to be more driving.
Okay, interesting. So, all right. Are there differentiating factors between critical energies turbo machinery versus conventional ORC systems? And are there innovations that your company has done within these modular units?
We are employing metal 3D printing in the manufacture. So one of the reasons why we chose the power class we did is it's the largest diameter rotors you can print on existing metal 3D printers. The metal 3D printing allows us to move faster on an iterative basis. So we can get complex geometry, blade geometries without going through quite as much, steps or processes. If you're doing a very large turbine set, your integration of your blades, your individual blade manufacturing can be quite complex. And we're keeping it a bit simpler by staying to a smaller diameter rotor and offering the opportunity to metal 3D print. That's kind of one of our advantages, you could say. The fundamentals of what we're doing we're not reinventing the wheel of physics. We're not changing anything fundamental. It's just from a scratch physics approach from the basis of physics of how do you design a thermodynamic cycle of a power plant and how do you design the turbo machinery pack that goes with it.
I just have to ask this. How did you come up with this business model, this concept?
Yeah.
How did you get to this point?
The Raptor rocket engine is turbines, compressors, and heat exchangers. So working on a rocket engine is basically working on a power plant. And there are 33 engines on the base of a super heavy booster. That's 66 turbines all spinning at the same time to thrust a super heavy rocket up, the super heavy booster of a Starship. So the ability to modularize power is something that's already being done. You look at data centers. There are data centers that have over 30 gas turbines all operating in parallel to power the data center. So it's not anything new to do this in that chunkable size, just no one has done it for geothermal.
Okay, so if we look at some of the power plants around the US, for example, do you think a lot of them are working at below their footprint, designed footprint. How important is this modularity component?
The modularity offers flexibility in projects and allows us to make
Yeah.
the same product repeatably for a variety of customers. So we are, if you're a 20 megawatt project or a 50 megawatt project, I make the same unit. Compare that to the other, projects. You either have to size your project very specifically to exactly what you can order for a turbine, or you're going to be ordering a unique bespoke turbine project. And the supply chain to do it is now sourced project by project. They source the components to the site. We are building our units in a factory, so we're sourcing our supply chain to our factory. That allows us to streamline the supply chain and deliver the same equipment to a variety of customers, and it kind of detaches the two, so that we can work on our supply chain. We build repeatability with our suppliers, so we order the same equipment over and over again in a way that they have confidence that we can get pricing down, and then we can pass that savings along to our customer.
I love it. Okay, so your website highlights the importance of critical turbo machinery in unlocking geothermal's potential. Can you walk us through what makes your turbo machinery design so pivotal? And I think you've hit on the scalability, but maybe you can re-emphasize this point.
We can hit the same thermodynamic efficiencies as our competitors at a smaller scale because we're still multi-megawatt. If you look at this is getting in the weeds, I apologize.
You're fine.
Turbo machinery inherently scales. The larger you go, the more efficient the turbine can be. And so historically, people have been trying to go bigger, bigger. You think then like that's one side of it. So like in that curve, the 10 kilowatt or 100 kilowatt turbines are significantly less efficient than a 1 megawatt, 10 megawatt, 100 megawatt. You get diminishing returns when you get about that. We found around the knee of that single digit megawatt curve. So from single digit megawatt to 100 megawatts, the difference in thermodynamic efficiency of your turbine is relatively moot. The difference between like a 2 megawatt and a 200 kilowatt is big still. You're talking about a pretty significant jump in efficiency. And part of that is the design choices. Smaller turbine packages and our power outputs usually result in different design of turbines than the larger. When you go larger, you end up in a space where your shaft speed and your power class puts you in multi-stage axial, and those are just inherently a more efficient design than a radial of those kinds usually can be in that space, or a screw expander, for example. So you're in a power class where we're getting efficient, but we're staying with manufacturing methods where we can make it on existing machinery that's readily available. When you stay under a meter in diameter, you can make the entire rotor single machine blisk or a metal 3D printed that allows you to stay really, really cheap. Like you have a lot more opportunity for machine shops that can do it than if you're moving to like more complex geometry turbo machinery. That's like one of our advantages. And then it's like the repeatability. We're making the same thing over and over again, ordering the same equipment. And this is like, I look back at SpaceX. The Saturn V had 5 engines on it, the F1 engine. Those engines are incredibly big, incredibly complex to make. They did it because they had effectively infinite money compared to what we do now for a similar size project back in the 60s in the development of Saturn V. The SpaceX approach was, we're going to start with what machine shops can make easily for parts. We're going to start with what metal 3D printers could print. And we're going to design an engine that is a chunkable amount that's easy to make with the off-the-shelf equipment that we can make it with. And we're going to make a lot of them. Then the price got really low because the same technicians were doing the same process, making the same parts over and over again. And you refine that process to make it really, really repeatable, high volume thing. We're doing the same thing to power plants. It's like, how do you take this the other direction of building a lot of the same thing is how you get really, really cheap. And there's like a valley of death there in terms of manufacturing. Yeah. If you look at like systems, like nuclear is a great example. In the 1950s and 60s, they were expanding the development of nuclear reactors, and they're still built on site piece by piece, single projects. So they found the way to drive costs down was to make them bigger and bigger. So they went to gigawatt projects. That's one direction you save the cost. The other direction is by making a lot of the same thing that's smaller. Think cars, right? Automobiles are on the order of like 500,000 units a year from the same factory in a repeatable process. Semi-trucks are like around 30,000 units a year. We need a bit like there's a gap there that you kind of have to hit one or the other. And if you're designing your plant to still be built on site piece by piece, you inherently want to go bigger and bigger with your plant, which is what's happening in geothermal. These 50 megawatt ORCs is the new direction everyone's going. We see it going the opposite direction on our end. We go smaller and build a lot of them. And that's how we hit massive cost savings and the ability to satisfy a lot of industry.
I buy into it, and I dig this. This is very interesting. So Critical Energy has already built and demonstrated a miniature power plant. Can you share a little bit about those details and
Yeah,
what that milestone meant for your team and what's next?
we have spun, so we built and are operating a 50 kilowatt miniature power plant right here in Los Angeles. It's we have an artificial heat source simulating a geothermal heat source, but it allows us to. We've spun a turbine, we've generated electricity, we've kind of proven the whole system. That was a huge unlock for the team because it was like the first time we've ever gone full stop heat to electricity conversion. And so you learn every step of the way. Like as stupid as it sounds, when you bring a whole new team together and you try and learn how to build a power plant, little things like how do you build a fluid loop that doesn't leak are like things that we get to learn at this scale when it's simple and easy before we scale up to larger infrastructure and larger projects. And we learned how to create a heat source and a cooling unit, how to extract, transfer heat, how to evaporate and condense a working fluid in a cycle. We're able to learn at this scale and basically prove operationally we have the ability to turn on a system and evaporate and condense. And then how to spin a turbine with that system in place, how to hand off between the bypass around the turbine to spinning up the turbine itself and generating electricity. So that was really good learning for their team that scales really well to our next projects. We're going to be installing another one of these 50 kilowatt units at a customer site next year. So we'll be hopefully, fingers crossed, doing electrons on a geothermal resource next year.
I love it. That's very exciting. Okay, so you've been doing this for quite some time now. So what are the biggest technical, maybe you could even talk about regulatory hurdles that are facing geothermal expansion in general that is impacting critical energy, and how are you choosing to address them?
Yeah, I think you might even be a better person to answer a lot of the question than me. The regulatory hurdles primarily impact the developers and how do you get projects going? How do you get the leaseholder rights? How do you get permitting in place? How do you get a grid interconnect agreement in place? On our end, we're kind of like the benefactor if it goes well, in that we have more ability to sell plants into that. So it does directly impact us, but it's kind of through our customers more than our road there. As you can imagine, as an early stage startup, we're trying to figure out how to navigate this as well.
Yeah.
Do our part. The ability that we have of bringing a bunch of, I think I'm basically the first SpaceX team that is coming into the geothermal world and trying to make a difference here. So hopefully we can bring a new angle, a new story, that can help with new publicity as we grow in that frame, in that lens, and then we'll be able to help with a bit more of the conversation.
Okay. So for example, your project next year, will you be putting electrons on the grid for your project?
For the 50 kilowatt, no, it's too small to be worth it for that.
Yeah.
But we're designing our first multi-megawatt unit right now.
Okay.
We'll be deploying that in the near future as well.
Okay.
Sometime in either late 26 or early 27, we'll be likely to be deploying our first 2 megawatt unit.
So is your first unit going to power something locally?
That one might be grid tied. It might be behind the meter operations.
Okay, got it.
Yeah.
Okay.
Yeah, there's opportunity to offset parasitic load with that. There's opportunities to power local operations, think drilling operations.
Yep.
You are using a well you flow tested to power your drilling of your other wells.
100%,
And then there are facilities that exist today that have grid tie that is more capable than their current plant can do, because they've seen a decline in the resource. There's plants that have been re-upped that have new wells. There's opportunities for us to install and produce more power for them from their new wells and use that power on site.
Yeah.
Or through their grid tie they already have.
How do you envision scaling critical energy systems globally, especially in regions with limited infrastructure?
If a drill rig can get there, we can get there. Our units are shipping container sized, so that any truck that can get there with a drill rig, we can get there too. And our footprint of our sites are very compact, such that the drilling operations platform is a substantial size to build our plant on as well. So that's what helps us grow globally. We very much intend to service the entire world. We're not looking to be just a domestic partner here. So I'm excited about opportunities for projects internationally, and as you can imagine, a lot of the geothermal activity today is international.
So what partnerships or collaborations have you established so far, and what have been the most impactful?
Yeah, I met Tim in October in Reno, 2023, Tim Latimer,
Okay.
and that was kind of what kicked off a lot of this was the chance to talk with Fervo and realize where they're at with their projects and what they could benefit from. I've continued to build a relationship with Tim and the Fervo team over time. They're a great opportunity for us. I've also been working with a lot of the other US-based companies. So Zanskar, Quaise, XGS, Sage, Rototherm. You can think of the gambit of groups that are kind of doing new geothermal projects, Power Planet, and a few of the others that are more recent to the scene as well. And then we're currently working on a lot of our outreach internationally as well, to some of the groups working on projects in Australia, in Europe, in Iceland, and we'll be expanding into Indonesia and Kenya as well, and
So
Turkey, of
looking
course.
ahead, what does success look like for critical energy in the next 5 years, and what impact do you hope to have on the energy landscape?
Yeah, success for us would be to deploy tens to hundreds of megawatts at commercial sites around the world of our units operationally creating grid scale power. That's what we're really kind of aiming for, and we hope to scale up to help geothermal grow to be one of the major dominant energy sources on Earth, and that we have the production line to actually supply that. Yeah, that we can do tens of thousands of power plants and gigawatts per year is the
Love
target of
that.
what Critical wants to do.
Love that. Okay, my final question. This is one of my favorite questions, is I really like to know what a typical day looks like for people, and I want to know what it looks like for someone running a company like yourself inside a critical energy.
Yeah. I'll answer that, I guess, two slightly different ways. One is for my team, because it's a very, very different landscape than for me personally. We're in Los Angeles, so we're here in sunny Southern California. The weather is, other than today where it's actually raining, it is normally beautiful, 70, sunny. And so we're like in an old industrial space that used to be, I think I want to say a Northrop building in the 1950s, making aircraft parts. So it's like brick, wood, vaulted ceiling industrial space. We built our power plant right here. It's big roll up doors that we open to the air and enjoy the space. So it's a good vibe. We're right next to a brewery, which is kind of fun. For me personally, it's how did I build a team, build a community here? We're half ex SpaceX, but also half not. So there's a lot of breadth of engineering backgrounds here. We eat lunch together as a team every day at some tables outside in our area. I personally, as you can imagine, as CEO, spend most of my time in emails and meetings like this. That's about exclusively what I do, and then lots of travel to customers, investors, opportunities like that. My world now is I'm a communicator. I just try and initiate things. I see my job as I'm doing the best I can if I am helping other people maximize their jobs, doing their work the best they can. I'm trying to help leverage them. So enabler, I guess you could say. A
I
good word. Yeah.
I love it. Your story is so fun, very unique. I can't wait to hear about your success in the coming years. Okay, so I want to thank you, Spencer, and I want to thank all of our listeners for joining us on this episode of Geothermal Unleashed. I hope today's conversation with Spencer has offered fresh insights and sparked new ideas about the future of geothermal energy. As we continue to navigate the energy transition, it's clear that geothermal has a powerful role to play, one that's just beginning to be fully realized. So until next time, keep challenging the assumptions, exploring new frontiers, and working together to unlock the full potential of geothermal energy. Thank you.